In this lesson, you will learn about buffers. Please read the OER textbook, chapter 15.2 for more details. What is a buffer solution? A buffer solution is the solution that can resist a large pH change when small amount of strong acid or strong base is added to the solution. A buffer solution composed of weak acid and its conjugate base. For example, weak acid, acetic acid, and sodium acetate, which is its conjugate base in form of salt. Or it can compose of weak base and its conjugate acid. For example, sodium carbonate, which is a weak base, and hydrogen carbonate, which is its conjugate acid. Let's take a look at example 1. Which solution is a buffer solution? If you consider choice A, the solution that contains nitric acid and hydrochloric acid, this solution is not a buffer solution because it's composed of strong acid and strong acid. For choice B, the solution that contains nitric acid and sodium nitrate, even though this is the salt of its conjugate base of nitric acid, however, nitric acid is not a weak acid. Therefore, this is not a buffer solution because composed of strong acid and its conjugate base. Now, choice C. When we consider choice C, it contains HF, which is a weak acid. But another solution that mix in this solution is sodium chloride. Sodium chloride is not the conjugate base of hydrofluoric acid, so this is not a buffer solution. Now let's take a look at choice D. D contains HF and its conjugate base, fluoride. It has hydrofluoric acid and fluoride ions, so this is an example of a buffer solution because contain weak acid and its conjugate base. Now let's consider choice E. There's a typo on choice E. Can you please fix the last compound to be NaH2PO4, please? And if you consider these two chemicals, you can see that sodium hydrogen phosphate and sodium dihydrogen phosphate, these two are not strong acid or strong base. So they consider to be weak acid or weak base. The one that has more proton, it would be the weak acid. And the one that have one less proton, it would be its conjugate base. Therefore, in this case, choice E would consider to be a buffer solution as well because contain weak acid and its conjugate base, or weak base and its conjugate acid. You will see more of this solution in the lab that we're gonna see in this week, because the lab this week, we are going to make sodium hydrogen phosphate and sodium dihydrogen phosphate buffer solution. How does a buffer work to resist pH change then? A buffer resists a large pH change by neutralizing added acid or added base. Let us take a look at a buffer solution that contains a weak acid, acetic acid, and its conjugate base, acetate ions. In this solution, because both weak acid and its conjugate base are present in one solution, they will be at equilibrium. For example, weak acid will react with water to produce hydronium ions and also its conjugate base as well. Vice versa, in the solution, the conjugate base that's present in the solution can also react with hydronium ion that is available to convert into weak acid as well. Now, when the strong base that contains hydroxide ion is added to a buffer solution, the species that will react with hydroxide ions would be the weak acid that is available in the buffer solution. The weak acid will neutralize added hydroxide ions from the strong base and convert into water and its conjugate base. Therefore, at the end of the reaction, you will see that the amount of weak acid will decrease and the amount of its conjugate base will increase because of this neutralization reaction. When the strong acid is added to a buffer solution, the added strong acid will produce hydronium ion, which will react with the conjugate base that's present in the buffer solution by neutralization reaction. The conjugate base will react with hydronium ion to produce its weak acid. Therefore, over time, you will see that according to the neutralization reaction, the amount of conjugate base will decrease and the amount of weak acid will increase over time if the strong acid is added to a buffer solution. When we look at a buffer solution after addition of the strong base, we can see that because the amount of the conjugate base is higher than amount of weak acid, therefore the pH of the buffer solution will slightly increase because there are amount of conjugate base than weak acid. However, if you look at the buffer solution after the addition of the strong acid, this solution here contains more of the weak acid than its conjugate base. Therefore, the pH of the buffer solution will slightly decrease. Recall that the pH is the inverse log scale of the amount of proton. Therefore, the more proton, the pH value will decrease. So that means if the solution is more acidic, the pH will be low. If the solution is less acidic, then the pH will be high. Note that as long as the amount of added acid and base is significantly small, the pH change of the buffer solution will also be small as well. However, if the amount of added base and added acid is more than the amount of conjugate acid and base in the buffer solution, then those added acid and added base can destroy a buffer solution. There are 3 ways to prepare a buffer solution. You are going to see the same 3 methods in lab 2 when we prepare for phosphate buffer. In the previous example, we see the buffer solution that contain acetic acid and its conjugate base, acetate ions. In example 2, we are going to look at how to prepare a buffer solution that contain acetic acid and acetate ion, similar to the example that we went over previously. The concentration of a buffer that we are going to prepare today would contain 0.5 molar of acetic acid and 0.5 molar of sodium acetate. This 0.5 molar means that in 1 liter of the solution is contain 0.5 mole of acetic acid. Same for 0.5 molar of sodium acetate as well. In 1 liter is contain 0.5 mole of sodium acetate. For method 1, you can prepare a buffer by mixing 2 solutions. For example, if you have a stock solution of 1 molar acetic acid and 1 molar of sodium acetate, if you take 0.5 liter from each solution and mix them together, these 2 solutions then will become 1 liter solution mixture. And you will see that as the solution is mixed, the concentration of these 2 will be diluted in half as well. Therefore, at the end, the solution will contain 0.5 molar of acetic acid and 0.5 molar of sodium acetate. And the total number of mole of acetic acid and sodium acetate would be 0.5 mole in 1 liter as well. If we don't want to prepare buffer from already prepared solution, the next thing we can do is mix the amount of acetic acid and sodium acetate together by weighing them. For example, to make 0.5 mole of acetic acid in 1 liter, we would need 30 grams of acetic acid. And to make 0.5 mole of sodium acetate in 1 liter, we will need 41 grams of sodium acetate. This amount comes from the fact that you are going to convert these grams into mole by using molar mass, and you can mix them together and then add water to it until the solution reach 1 liter solution total. Therefore, this solution will also contain 0.5 mole of acetic acid and 0.5 mole of sodium acetate in 1 liter, which is identical to the previous method that we just prepared. Method 1 is the simplest and the straightforward method compared to 2 and 3. Method 2 will rely on neutralization reaction between weak acid and strong base. The reaction that we are going to take a look at is the reaction between weak acid, acetic acid, and a strong base, sodium hydroxide, that produce sodium acetate and water. In order to before we can prepare for buffer solution, the easiest way to understand this is by looking at the amount of mole that react and to see what is left over at the end. The table that I set up here is not a rice table, it's RICF. F is referred to final, which is in this case is the stoichiometric ratio. So that means the final will not be at equilibrium. Therefore, in this case, the RICF table, the unit that you will need to plug into here have to be in the unit of mole. You will see that the difference between RICF and RICE, the difference is the unit that you plug into each of these tables. For the rice table, the unit that you need to plug in would be in the unit of mole per liter. The easiest way for me to remember this is that the E has leg, so that's why you need to divide by liter. But F doesn't contain any leg, so that's why you get rid of that liter, so it's just going to be just mole. And again, the reason why we are using RICF because this is a neutralization reaction. Everything reacts with mole to mole ratio, and at the end, it will not be at equilibrium. To make a buffer solution that contains the same molarity that we prepare from the method 1, first we will need to react acetic acid with sodium hydroxide. And at the beginning, the amount of the product will be 0. I'm going to ignore water in this case. Next, let's consider change. Change for the RICF table will not be the same as RICE. It will not be X because we will know the known amount of change by looking at the species that is the limiting reactant. In this case, if you compare between the amount of acetic acid and amount of sodium hydroxide, you can see that the amount of sodium hydroxide that react with acetic acid is much smaller. Therefore, in this case, the sodium hydroxide is going to be our limiting reactant, which mean that at the end of the reaction, the sodium hydroxide will be all consumed. So the change of this reaction would be negative 0.5 mole that come from sodium hydroxide amount that we have. And in order to neutralize this 0.5 mole, we will also need 0.5 mole of acetic acid as well. And because the reaction is 1-to-1 ratio, therefore the sodium acetate that is produced going to be 0.5 mole as well. At the end, what left over, that would be the final. In this case, the leftover species at the end would be 0.5 mole of acetic acid. We will have 0 mole of sodium hydroxide left, and it would be 0.5 mole of sodium acetate left at the end. As you see, this solution at the end contains 0.5 mole of acetic acid, weak acid, and 0.5 mole of sodium acetate, which is its conjugate base. Therefore, this solution is considered to be a buffer solution because contain weak acid and its conjugate base. In the lab, you can do this by obtain a beaker and then add 1 mole of acetic acid and 0.5 mole of sodium hydroxide and make sure that the total amount of volume at the end would be 1 liter of the solution. And after these two species react or neutralize with each other, at the end you are going to get a 1 liter solution that contains 0.5 mole of acetic acid and 0.5 mole of sodium acetate, which is exactly what we see in this RICF table. Method 3 is very similar to method 2, except we are going to react weak base with the strong acid. Set up RICF for the neutralization reaction because at the end, one of the species will be all consumed. It will not be at equilibrium. And in this case, we are going to react weak base, sodium acetate, with strong acid, hydrochloric acid. When the weak base accepts proton from hydrochloric acid, it will become its conjugate, weak acid, acetic acid. And another species that will produce is salt, sodium chloride. From the salt section, we learned that sodium chloride is pH neutral. So that means in this case, we will not have to worry about sodium chloride because sodium chloride will not affect the pH of the solution. At the beginning or at the initial state, we will start with 1 mole of sodium acetate and 0.5 mole of hydrochloric acid. Again, at the beginning, the number of mole of product would be 0. And if you look at the number of mole and compare between mole of sodium acetate and hydrochloric acid, we can see that the number of mole of hydrochloric acid is less than number of mole of sodium acetate. Therefore, in this case, hydrochloric acid would be the limiting reactant, which means that it's going to be all consumed, which means it's going to decrease by 0.5. It's going to be used up. And in order to react with this 0.5 mole of hydrochloric acid, it requires also 0.5 mole of sodium acetate to react. And the amount of acetic acid that will be produced would be 0.5 mole of acetic acid. Therefore, at the end, what we have left would be 0.5 mole of sodium acetate and 0 mole of hydrochloric acid and 0.5 mole of acetic acid. And if you look at the final state, you see that at the end, the only species left in this solution would be sodium acetate and acetic acid. Again, because this solution contains weak base and is conjugate acid, this solution would consider to be a buffer solution. For method 3, in the lab, we can obtain a beaker and add 1 mole of sodium acetate and add 0.5 mole of hydrochloric acid. Make sure that the overall solution would be in 1 liter. So if it's not 1 liter, we just add more water to make it to be 1 liter. And after these two species react or neutralize with each other, at the end, we are going to end up with 0.5 mole of acetic acid and 0.5 mole of sodium acetate in 1 liter of the solution, similar to what we see from the RICF table. Next, we are going to learn about how to calculate pH of a buffer solution. When we calculate for a buffer solution, we are going to use Henderson-Hasselbalch equation to help us to calculate the pH, which pH equal to pKa plus log of the conjugate base divided by conjugate acid. Again, this conjugate acid base have to be a conjugate acid base pair, which means these two species will be different by 1 proton. Recall that the P is the negative log scale, which means that pKa would equal to negative log of Ka. Now let's take a look at example 3. Example 3 asks to calculate pH of the solution that contains acetic acid and sodium acetate. This solution contains weak acid and its conjugate base. Therefore, this solution is a buffer solution. Because this solution is a buffer solution, so we are going to use Henderson-Hasselbalch equation to help us determine pH of the solution. So the pH will equal to the pKa, which is negative log of the Ka value plus log of the conjugate base over weak acid. If you calculate for the pKa value, the negative log of Ka will come out equal to 4.74. Add this number to log of 0.45 over 0.75, it would equal to negative 0.22. And overall will give you the pH of 4.52. Next, I would like you to pause the video and complete example 4, 5, and 6 and resume the video when you're done to go over the answers. Now let's compare your answer with mine. The solution in example 4, 5, and 6 are the same buffer solution that we did as example 3 because it contains weak acid, acetic acid, and its conjugate base, sodium acetate. So we are going to use Henderson-Hasselbalch equation to help us calculate for the pH. We already obtained the pKa from the previous example, so I'm going to keep using the same pKa throughout because the acid that we use are the same acid. For the concentration of the weak acid and its conjugate base, example 4, they both are the same. Example 5, they both are the same as well, 1.5 molar. And example 6, we have more of the weak base than its conjugate weak acid. So if you plug in all the value, you will get pH example 4 equal to 4.74. And for example 5 would be 4.74 as well. Because when these two are equal, it will equal to 1, log of 1 equal to 0. So that's why the pH would equal to pKa in this case. For example 6, when you plug in all the value, you will get pH of 5.74. Next, we will look at the effect of the concentration of weak acid and its conjugate base in each of these buffer solutions. When we consider example 3, we can see that the amount of weak acid is higher than the amount of its conjugate base. And because this buffer solution has more weak acid, therefore the pH would be lower than pKa. Next, when we consider example 4 and 5, we can see that the amount of the weak acid and its conjugate base are the same. And when the weak acid equals to conjugate base, the pH will equal to pKa. As explained earlier, when the concentration of acid and base are the same, log of 1 will equal to 0, therefore pH will equal to pKa. For example 6, we can see that we have more of the conjugate base than the weak acid. In this case, when we have more conjugate base, the pH will be higher than pKa. A buffer range is the maximum pH range at which a buffer is effective. If you look at the Henderson-Hasselbalch equation, the buffer range will range from the ratio between conjugate base and conjugate acid from 0.1 to 10. Therefore, if you plug those ratio in, you will get the pH range from pKa plus minus 1. Outside this range, the buffer will not be effective. And the buffer will be most effective when the concentration of weak acid equal to its conjugate base concentration, which means that the buffer will be most effective when pH equal to pKa. And not only that, a buffer is the most effective when the concentration of both conjugate base and weak acid are at the highest concentration. Even though a buffer solution can resist a large pH change, it will work only when small amount of strong acid and base are added to the solution. If the amount of added acid and added base is more than buffer can handle, it will destroy the buffer. Therefore, a buffer capacity is the mole amount of acid or base that can be added without destroying the buffer. Let's take a look at example 7. Which of the buffer solutions from example 3 to 6 previously is the most effective buffer? I would like you to pause a video and go back to example 3 to 6 and choose the buffer that is most effective. The buffer that is the most effective is from example 5, 1.5 molar acetic acid and 1.5 molar sodium acetate. This is because the concentration of the conjugate base is equal to the concentration of the weak acid, and also both concentrations are at the highest concentration. Example 8 is an example of how to choose a buffer solution. The problem giving us the 3 ionization of phosphoric acid, first step, second step, and the third step, with different Ka value. For the polyprotic acids such as phosphoric acid, the first ionization would be the greatest extent ionization than the second and the third. This is because the first one is going from neutral molecule to become an anion. This anion would most likely to hold on to its proton, and it's harder to release that one proton. That's why the ionization constant will be less. And same as for the third one as well, as it becomes more negative, it's going to be harder to give off the proton. So that's why the ionization constant will become even smaller. Now, if we look at the acid ionization compared with the 3 choices that is given, we can see that choice A would match with the first ionization, and choice B would match with the second ionization, and choice C would match with the third ionization. The only difference is that all of these contain sodium within the compound. Sodium are here to balance the negative charge of these ions, because in nature, this ion will not be a free ion. It will come with a positive charge to make it balanced. And the sodium ion will not affect the pH of the buffer solution, because from the previous chapter that we learned about salt, sodium ion is pH neutral ion. To find the best choice of a buffer with pH at 7, we will need to look at the buffer range. We see that the buffer range is going to be between pKa plus or minus 1, and the best or the most effective one is when pH equal to pKa. Therefore, in order to choose which one it is, we will need to look at the pKa for each of these dissociation. When we take negative log of Ka value, we are going to get pKa, and the choice that is close to pH 7 would be the second ionization or the second dissociation. Therefore, the best combination of the buffer would be B. Next, let's take a look at a buffer capacity example from example 9. Which action would destroy the buffer containing 0.1 molar hydrofluoric acid and 0.05 molar sodium fluoride in 1 liter of the solution? From the given information, we know that this solution contains 0.1 mole of hydrofluoric acid in 1 liter solution and 0.05 mole of sodium fluoride in 1 liter of the solution. For choice A, adding 0.05 mole of sodium fluoride will cause the total mole of sodium fluoride to increase to 0.1 mole of sodium fluoride. This action will not destroy the buffer solution. Instead, this action will increase the effectiveness of the buffer because now the total of mole of conjugate base is equal to its conjugate weak acid. Therefore, when these two are equal, the buffer will be most effective. Action B, adding 0.05 mole of hydrofluoric acid. Therefore, the total mole of hydrofluoric acid in the solution would be 0.1. Action B will only decrease the effectiveness of the buffer, but it will not destroy the buffer because this buffer solution still contains weak acid and its conjugate base. Now let's take a look at action C, adding 0.05 sodium hydroxide. Sodium hydroxide is a strong base. When sodium hydroxide is added, the hydroxide ion, which is 0.05 mole, will react with the weak acid within the solution. We will see that the weak acid mole that we have is 0.1 mole of weak acid. Therefore, in order to neutralize 0.05 of hydroxide, we will also need 0.05 mole from hydrofluoric acid. Therefore, the total mole at the end after the neutralization reaction, the total mole of hydrofluoric acid will equal to 0.05 mole. And the total mole of the fluoride ions in the solution will increase to 0.1 mole. Action C only decreases the effectiveness of the buffer. However, it doesn't destroy it because this buffer still contains weak acid and its conjugate base. Action D, adding 0.05 of the strong acid HCl into the buffer solution. Strong acid will give off proton that can react with the conjugate base fluoride ions. 0.05 mole of proton from the strong acid will react with 0.05 mole of conjugate base that available in the buffer solution. Therefore, at the end, after the neutralization reaction, the concentration of the conjugate base, sodium fluoride, will become 0, and the weak acid that is produced combined with the original weak acid that is present in the solution, it will be the total of 0.15 mole. We can see that the result from action D, we have no weak base left. We have only weak acid. Therefore, this solution is no longer a buffer solution because it contains only weak acid but no more its conjugate base. Therefore, in this case, action D would be the action that would destroy the buffer. Next, we will take a look at how to calculate pH of a buffer solution before and after the addition of strong acid and strong base. Example 9 gives a buffer solution consists of these two species. Which one is weak acid and which one is conjugate base? First, you will need to look at which one has one more proton and which one have one less proton. This species here has one more proton, so this species would consider to be weak acid. And the other species that have one less proton replacing by potassium, this would be weak base or its conjugate base. Again, the reason why we include potassium because once the weak acid loses its proton to become its conjugate base, it will become the CH2 minus. And again, in nature, this CH2 minus will not exist by itself, it will need to come in a neutral form, which is going to pair up with other cations such as potassium, sodium, or lithium, or other cation. To calculate pH of this buffer, again, we are going to use Henderson-Hasselbalch equation. Plug in all the value, you will get the pH of 3.672. Next, we are going to calculate pH of this buffer solution after the addition of 0.5 liter of 0.01 molar of hydrochloric acid into the original buffer. The added acid will react with available weak base in the buffer solution in a stoichiometric ratio. Therefore, we will first need to find mole of each of those species available in the solution. To calculate for mole, use the volume that is given for each species, multiply by their concentration. You will get the mole that available for each of those. After the calculation, you will see that the number of mole of the added proton from the strong acid would be 0.0050 mole, and the number of mole from the weak acid available in the buffer would be 0.975 mole, and the mole of the weak base available in the buffer would be 0.825 mole. The next step is to set up the neutralization reaction and set up the RICF table. Again, the unit that go into the RICF table have to be in the unit of mole because the acid and base are going to react with the stoichiometric ratio. The added acid proton will react with the base available and convert this into the weak acid. At the beginning, the initial mole of each of these species will come from the number of mole that we just calculated from the first step. When the proton react with the weak base, you will see that the number of proton is a lot less than the weak base. Therefore, the proton would be the limiting reactant. The amount of the proton from the strong acid will decrease by 0.0050, which means that it's going to be all consumed at the end. And in order to neutralize this amount, you also will need the same amount for the weak base as well. And the amount of the weak acid that will produce will be the same ratio, will be the same amount, which is 1-to-1 ratio. Final state would be whatever left over from initial and change. For the amount of proton would be 0, amount of weak base would be 0.82, and the amount of weak acid that produced would be 0.98. Consider the RICF table. You can see that this solution still contain weak base and weak acid. Therefore, this solution is still a buffer solution. To calculate the pH of a buffer solution, we will use Henderson-Hasselbalch equation, which require the concentration of weak base and weak acid. The concentration of both weak base and weak acid can be calculated from the amount of mole divided by the total liter of the solution. In this case, the amount of mole of weak base that left would be 0.82, and the volume that available would be, before at the beginning we have the volume of the buffer, which is 1.5 liter, and when you add the 0.5 liter of the acid, the total volume will come out to be 2 liter. Therefore, the concentration of weak base will equal to 0.41 molar. Do the same thing for the concentration of weak acid. Plug in the leftover mole of the weak acid, divide by total volume, which is 1.5 plus 0.5. You will get the concentration of 0.49 molar. The final step is to calculate pH. By plugging in the pKa plus log of conjugate base over conjugate acid, you will see that the pH of this solution will come out to be 3.667. Now, if you compare the pH after adding the acid into the buffer solution to the original buffer pH, you can see that the buffer after adding acid will slightly be lower than the original buffer because the solution becomes more acidic. You probably noticed that in the Henderson-Hasselbalch equation, the conjugate base is divided by the weak acid concentration. Therefore, if you're looking at the concentration of these two are divided by the same volume. So what if, instead of plugging in the concentration, what if we plugging in the number of mole instead would give us the same answer? Let's take a look at it. When we use the leftover mole and plug into the Henderson-Hasselbalch, you will see that it will still give us the same identical pH value. This is because both weak base and weak acid are in the same volume. Therefore, when you convert into molarity, they are going to be divided by the same value. And if you plug in the concentration of each of those two into Henderson-Hasselbalch, you can see that the volume will also be cancelled out. Therefore, we can use just the number of mole instead of the concentration. In conclusion, we can use number of mole instead of concentration in the Henderson-Hasselbalch equation as long as all the species are in the same volume. Next, we are going to take a look at pH calculation after the addition of the strong base. When we add the strong base, the added base hydroxide ions will react with the weak acid that available in the buffer solution in the stoichiometric ratio. Therefore, our first step is to find number of mole that are available in the solutions. To find out mole of hydroxide ions, the mole of hydroxide ion will come from the volume of sodium hydroxide multiplied by its concentration. You will get mole of hydroxide ion to be 0.0050 mole. And because we are going to add this hydroxide ion in the original buffer, and we calculate the original buffer mole of weak base and weak acid already, so here are the number of mole of those that we calculate from the previous section. Next is to write out the neutralization reaction and set up the RICF table. The added base hydroxide ion will react with weak acid available in the buffer solution to produce its conjugate base and water. Next, plug in the available number of mole at the initial, and the limiting reactant for this reaction would be the hydroxide ion that have the least amount compared to the weak acid. So the amount of mole of hydroxide ion will always be consumed. And in order to neutralize that added base, we are going to use the same amount of weak acid available, and the same amount will be produced for its conjugate base. And the final mole would be whatever left from the initial and the change. At the final state, we see that the solution contains weak acid and its conjugate base. Therefore, this solution is still a buffer solution. So in order to calculate for the pH, we are going to use Henderson-Hasselbalch equation. We just saw from the previous example that as long as the weak acid and its conjugate base are in the same volume, instead of using the concentration, we can use the number of mole and plug it in, because when you convert into concentration, you are going to divide these two numbers by the same volume, and the volume will then be cancelled out. Therefore, in this case, we can just plug in the number of mole in each of those within the Henderson-Hasselbalch equation. And the buffer pH after adding strong base would be 3.677. Compare this buffer pH after adding hydroxide ions, we can see that it's slightly increased compared to the original buffer pH from part A. And again, the reason why it's increased because adding base, the pH will be slightly more basic and less acidic. Now let's take a look at question D. In order to destroy the original buffer solution, how many moles of sodium hydroxide will need to be added into the original buffer solution? First, you will need to know in the original buffer solution how many mole of each of those species are available. From the previous calculation, we can see that the original buffer contained 0.825 of the conjugate base and 0.975 of weak acid. So when we add sodium hydroxide in this original buffer, the sodium hydroxide will react with weak acid available in the buffer solution. In order to destroy this buffer, the amount of weak acid will need to be all consumed by neutralizing adding sodium hydroxide. Therefore, at least the number of mole of sodium hydroxide that we will need to add into this buffer solution will need to be at least equal to or greater than 0.975 mole. When the amount of mole of sodium hydroxide at least 0.975 mole is added, it will react with weak acid completely. Therefore, at the end of the solution, there will be no weak acid left, and this solution is no longer a buffer solution because it contains no weak acid. Now for part E, in order to destroy a buffer solution, we're gonna add hydrochloric acid. If hydrochloric acid is added to the original buffer, the species that will react with hydrochloric acid would be the weak base that are available. And in order to destroy this buffer, you will need to add at least 0.825 mole of hydrochloric acid or greater in order to consume of these weak base that are available. However, the problem doesn't ask for a number of mole. Instead, it's asking for the volume of hydrochloric acid that we will need to add. The problem gives us the concentration of hydrochloric acid. Again, whenever that you see uppercase M, please convert this unit into fraction form, which is mole per liter. We are going to use this number as our conversion factor because it allows us to convert between mole and liter. So I'm going to start with the number of mole that we need, which is at least 0.825 mole. And because we know that in 1 liter of the solution of hydrochloric acid is contain 0.45 mole of hydrochloric acid. The mole will cancel out, then you are going to convert liter into milliliter, and you will get the volume of hydrochloric acid equal to 18,000 milliliter. The volume of hydrochloric acid in milliliter have to come with a big number because if you look at this example, throughout this example, they are talking in a liter, which is a bigger unit than a milliliter. So when we convert it into milliliter, therefore our value will come out a huge number. Please practice more of this concept by doing the DIY on page 47. You can get help during the hangout session or office hour, and the answer key of this will be posted on Moodle. Thank you.